Hi, I'm Dahye Lee, a PhD student in Army Lab. Today, I'm going to talk about SeeSE3, Emergence of 3D Space in Vision Features from Google DeepMind. It is only on archive. This work arises from the Henry-Poncras hypothesis. Henry-Poncras hypothesized that a motionless being could never have acquired the concept of space. He would have had no reason to distinguish changes of position from changes of state, nor would he have been able to acquire it if his movement had not been voluntary. Nowadays, there are many vision foundation models. The authors of vision foundation models tried with a large amount of images, but they cannot move, so they are one of motionless beings, and the authors tried to test the Henry-Poncras hypothesis with vision foundation models. Although some vision foundation models train with videos, not images, they also watch the movement of objects passively, so they are also motionless beings. The author formulated the Poncras test based on Henry-Poncras hypothesis. Can a motionless observer, given only passive visual input, discover the structure of 3D space? In particular, does a vision model naturally organize its latent space in a way that reflects the spatial Euclidean group SeeSE3 of Euclidean transformations? Before this work, there are some research that utilize the vision foundation models for understanding 3D vision. Proof 3D research on 3D awareness of visual features. It proves the vision foundation models. To predict the depths and normals, and other research connect vision foundation models to high capacity decoders to extract 3D geometry information, such as camera pose and depths. Unlike previous research, SeeSE3 tests whether the feature space itself is organized to reflect Euclidean 3D structure. Visual feature and Euclidean structure have different properties. Visual features are high-dimensional and tied to visual content. Otherwise, Euclidean 3D structure consists of position and camera orientation, so it has only 6 dimensions, and it has homogeneity. So this research tried to figure out whether low-dimensional homogeneous coordinate system resides in the visual features. Let's move on to how SeeSE3 tests Poncras task. Before explaining what metrics the authors use, let's see the specific problem statement. The authors consider static scenes where the mapping from camera pose to an image is stable and well-defined. A moving camera observes the scene, then we can get images with camera poses across time t. And given the images, the vision foundation models output the features, and the goal is to determine if these features reflect the structure of Euclidean transformations the camera undergoes. To evaluate geometric awareness, they test the diverse vision foundation models on static scenes. Their evaluation covers specified raw pixels as a baseline and self-supervised representation models like DinoV2 and VJPA. And they also evaluated on generative models and video models and explicit geometry foundation models like Duster, which serve as an upper bound. So they evaluate for metrics for its foundation models to check whether the topology of the feature points locally respect the topology of SeeSE3. They evaluate the topological alignment and intrinsic dimensionality. And to test if the feature space is globally Euclidean, they evaluate linear equivariance, and the Poincare adapter. First, topology alignment evaluates the similarity between neighborhoods in the visual feature and camera pose spaces with the KNN alignment metric. Specifically, it calculates the proportion of shared care nearest neighborhoods between latent feature space and the 3D camera pose space. This is result of first metric. They evaluate the burst metric across both short and long temporal strides. So this axis is short strides and this axis is about long strides. Since larger strides involve greater viewpoint changes, so this allows us to assess global spatial awareness. Looking at the metric 1 result, models explicitly trained with geometric objectives achieve high alignment scores even at larger frame strides. Although most of these geometric methods typically rely on a dedicated decoder to rigorous camera poses, the findings reveal that the encoder itself structures its latent space to align with the underlying 3D pose geometry. This proves that geometric training implicitly shifts the encoder's feature manifolds without necessarily needing explicit decoding layers. And Dino V2 and Dino V3 exhibit remarkably strong topological alignment, significantly outperforming other baselines and raw pixels. On the other hand, video model showed significantly lower performance on this metric. That's because video models are naturally designed to learn temporal motion across frames. As a result, instead of focusing on fixed coordinates like where the camera is in 3D space, their features become heavily entangled with temporal context, focusing primarily on how frames connect sequentially over time. So consequently, they fail to form a stable, globally consistent spatial map of the static environment. Next, the second metric measures the local intrinsic dimensionality of the feature space using two estimators, maximum likelihood estimation and 2NN. Since camera motion in a static scene has 6 degrees of freedom, an intrinsic dimension close to 6 suggests that the feature space effectively captures the underlying physical degrees of freedom. And the third metric, which evaluates linear equivariance, they test whether the feature space is natively flat and globally Euclidean by fitting a simple linear regressor W to predict relative 60 pose changes directly from feature difference. This is the results for metric 2 and metric 3. First, under metric 2, most encoder use feature representations with an intrinsic dimensionality clustered around 6. This closely aligns with the 6 physical degrees of freedom of camera motion in the 3D space, confirming that latent spaces naturally capture the true underlying spatial parameters. While most encoders cluster around an intrinsic dimension of 6, Dino V2 and Dino V3 exhibit higher intrinsic dimensions. The authors explain that this higher dimensionality reflects a much richer semantic manifold, which has expanded beyond simple low-level pixel correlations. In other words, Dino's feature space captures complex high-level semantics alongside 3D camera geometry. However, when they evaluate metric 3 for linear equivariance, row feature differences result in negative R-square scores across almost all models. This indicates that while the latent space preserves the 6D-dimensionality, its manifold is natively curved and non-flat, meaning row feature vectors cannot be directly mapped to camera motion via simple linear operations. In summary, as shown of this picture, in this picture, metric 2 and metric 3 do not effectively differentiate between different vision encoders. This is because metric 2 is essentially too easy, as almost all models naturally exhibit an intrinsic dimensionality close to 6. On the flip side, metric 3 is too hard since no row feature space possesses an easily linearizable subspace that aligns directly with physical camera motion. This clear limitation of row features under metric 3 is precisely what motivates metric 4, where they introduce an adapter to unroll these curved manifolds. So metric 4 tests if a lightweight adapter can unroll the manifold into a locally Euclidean 3D coordinate space. Since row feature space is natively curved as shown in the results of metric 3, they train a lightweight Siamese MLP adapter Bisetta to unroll the feature manifold, mapping the latent displacement directly to 6D camera motion. And the authors call this adapter as Planck adapter. This is the result of metric 4. When applying Planck adapter, innovate 2, this is orange line, reaching a tested scale of approximately 0.65. This high score implies that while the row feature space is natively curved, its latent space implicitly contains a locally Euclidean submanifold isomorphic to SeeSE3. Moving on to the generalization and scaling part, to evaluate how well these learned geometric structures generalize, the authors trained the Planck adapter exclusively on ScanNet and tested it zero-shot across 31 completely unseen rooms. The results show strong zero-shot transferability, demonstrating that the adapter spatial representations are not overfitted to the training scenes. Furthermore, the paper highlights the key scaling behavior. The authors observed that a model's geometric awareness, its ability to encode 3D spatial structures, grows continuously as model scale and data volume increase. This confirms that large-scale visual pre-training not only enhances a model's intrinsic understanding of 3D geometry. Building on this previous experiment, the authors tested whether latent space navigation is possible. Beyond proving geometric awareness, they demonstrate a practical application enabled by their framework, latent space navigation. Instead of performing computationally heavy 3D reconstructions, their model allows an agent to imagine and predict the feature representation of a destination frame simply using vector arithmetic. Based on the formulation introduced earlier, the target feature G hat T plus S can be calculated as the sum of GT and the inverse Planck inverse transpose of W delta P. While this inverse Planck approach provides an extremely fast closed form geometric estimation from the linear operation, they struggle to only capture complex nonlinear errors or spatial drifts. To address this, a nonlinear network that is incorporated as a residual corrector to refine the fine-grained errors that occur when moving by the topic from the current state GT. To quantitatively evaluate navigation success, they perform a nearest neighbor retrieval task on a test set of unseen scene frames. Specifically, they query the test frames using the predicted feature hat GT plus S via L2 distance in the adaptive feature space, then measure pose error is denoted as hit at epsilon, which reports the fraction of retrieved frames whose relative pose falls below a threshold epsilon. Next, looking at the latent space navigation experiment, the authors compare three different navigation approaches: the baseline identity prediction, and the linear inverse Frankfurt term, and the learned attention corrector. Interestingly, while the learned attention corrector is better regression metrics like R-square, the closed form of inverse Frankfurt approach outperforms it in actual retrieval performance measured by hit at epsilon. This demonstrates that when the feature space correctly linearizes the SeeSE3 geometry, simple vector arithmetic is more direct and powerful for finding physical neighbors than applying the complex nonlinear corrections. Therefore, simply by following spatial movement rules, the model holds the potential to imagine unobserved scenes. Looking deeper into the cross-room evaluation results, the authors highlight three key findings. They test zero shot on 31 unseen target rooms. First, even in completely unseen environments, using only the pre-trained pseudo-inverse metrics achieves correct frame retrieval in roughly 60% of cases. This suggests that the vision encoders already encode the universal notion of spatial geometry. Second, when a lightweight regression is applied using a minimal amount of test environment data to adapt only the linear mapping, retrieval accuracy dramatically surged to 90 to 94%. Importantly, this process leaves the core adapter parameters frozen, adjusting only for minor geometric variations like room scale or focal length. Finally, this remarkable generalization is consistently observed across diverse backbones. This proves that the geometric manifold uncovered by the Frankfurt adapter is not an artifact of the specific model, but a fundamental property intrinsic to visual representation of physical world. Next, the authors also test on multi-step navigation experiment. They evaluate whether the model can execute a sequence of spatial transformations across multiple consecutive steps. For the methodology, instead of predicting a single-step displacement, the framework iteratively applies statewide camera pose shifts in the latent space, starting from an initial feature G0. The model updates its latent representation at each step using either vector arithmetic or the learned adapter, navigating along extended trajectory. In this picture, this confirms the feasibility of open-loop latent planning over extended passes. So the answer of the Hanley-Pankras hypothesis is yes. A motionless observer can discover space, but only up to a nonlinear unwrapping that a simple adapter can undo. And the author suggests some analysis of the experiment. First, probe design is important. They try to predict SeeSE3 matrix regression, but predicting 60 twists was better. And when predicting excellent post, the performance is not good. This indicated the denote V2 encodes the relational structure between views, and calculating difference after applying uh, adapter mapping, that is predicting calculating the difference after applying the adapter mapping is significantly better than applying mapping to the raw feature difference. This highlights why a simultaneous design is essential. It infers homogeneity. So bypassing both source and target features through the shared weight, it guarantees that both representations are mapped into the exact same metric space. Next, why does the adapter work so effectively? The authors explain that pre-trained vision backbones like DinoV2 already contain high-quality 3D spatial information. However, in raw feature space, this information is natively curved and folded due to complex visual vectors. The Puncture adapter acts as a lightweight geometric unroller by projecting features through a geometry aligned nonlinear space. It unrolls the natively curved manifold into locally Euclidean subspace. So this confirms that the adapter functions not as a heavy text-specific solver, but as a minimally intrusive key that unlocks a visual breakcode already latent within the backbone. Additionally, the author explains why predicting translation is harder. Predicting translation is harder than predicting the rotation. Rotation depends only on pixel coordinates and focal length. Thus, it is independent of scene depth, resulting in low variation. On the other hand, translation is depth dependent, so if the image has complex depth map, there are high variation. So rotation is significantly easier to decode than translation. And let's look at the model training analysis to see which training conditions are necessary for 3D geometric structure to emerge. The authors trained DinoV2 base from scratch with various hyperparameter variations, such as loss, the number of prototype, and batch size. Throughout the experiment, the topology maintained stable performance, whereas geometry was not well preserved depending on the training method. Among these, the authors identified that three specific training methods play a crucial role in performance. First one is Dino training consists of multiple loss terms. When the Dino self-distillation loss is removed, the performance of the topology drops significantly. This indicates that Dino self-distillation is essential for topological alignment. And second, when reducing the batch size 192 to 128, the topology drops to a level similar to that of model with random weight. This indicates that batch size is vital for topology. Finally, pre-trained DinoV2 achieves better geometry than their ablation models. The primary difference lies in the data scale. While pre-trained DinoV2 was trained on a massive dataset, ablation models were trained on only a single video. This suggests that data scale is the dominant factor for geometry. As the authors explain, metric scale requires statistical priors over object size that only diverse training can provide. In conclusion, this paper investigates whether vision features capture Euclidean space by evaluating their alignment with SeeSE3 rigid motions. Although standard encoders do not reflect this structure directly, a simple low-dimensional adapter can unroll the feature manifold to map feature changes directly to pose changes. Ultimately, these converged self-supervised models implicitly form decodable 3D space representations through passive observation alone. As a key limitation, this work focuses exclusively on static scenes without addressing Planck's classical distinction between changes of position and changes of state. Looking ahead, an exciting direction for future work would be extending their framework to dynamic scenes, because dynamic environments involve both camera motion and underlying physical scene dynamics. Applying this approach here could have uncovered deeper spatial temporal scenes. This is all of my presentation. Thank you. Is there any question? I have a question. Thank you for your